In today's video, I'm going to tell you how you can save energy in buildings by just tweaking or adjusting a few parameters. No new equipment, no new controllers, no new design control strategies, just adjusting parameters. And if you adjust those parameters during maintenance time, during service, then this energy efficiency initiative is for free. Because comfort control and energy efficiency control are two opposite things. Comfort control is here and energy efficiency control is here. And although we are designing new air handling units, supply temperature resets, supply pressure resets, we're staging chillers on capacity, we're doing all this sort of major software code changes, a lot of the fundamentals of comfort control are still finding their way into being reused for energy efficiency control. Bear with me. This will make sense if you watch this video through to the end. Before everything went virtual, I used to do these advanced control strategy courses in Melbourne City. Hire out a beautiful boardroom, I'd supply food and coffee, and it'd be a whole day thing, face to face, in a room, walking around. And there was always one or two BMS engineers that would argue this point with me. So I already know that 1 in 20 of you are not going to agree with what I'm going to say here. And I'm just asking for those of you that don't agree, just bear with me, watch this video through to the end and give me an opportunity to change your mind. All terminal units, VAVs, fan coil units, chill beams, induction units, package units, heat pumps, all mechanical terminal units that the heating cooling valve or the damper is controlled from a zone temperature sensor, those PID loops should be proportional only control, not proportional plus integral control. P only, not PI. Now I'm not talking about chillers and boilers and cooling towers and air handling units, the whole building. Most of those main systems, they should be PI control. I'm only talking about terminal units that have a zone temperature sensor on a wall in the zone, and that is controlling dampers and valves and things. So if you take your PID loop for that zone temperature control loop and you remove the integral control, you set the integral to be 0 seconds or 0 minutes, that will save energy. But we also need to adjust the proportional band and the set points for it to properly work. But I will get into that later on in this video. Let me first explain why integral wastes energy, and then we'll get on to what to do with the proportional band and the set points later on. To explain why integral wastes energy, I need to give you a very, very basic introduction to how proportional and integral works. And I'll make this very simple. So proportional band is a very simple thing. It's a straightforward mathematical calculation. It looks at the process variable, the temperature, and looks at the temperature set point, and whatever that difference is, the error, it just calculates where the valve should go. So for example, if you have a proportional band of say 2 degrees Celsius, and the difference between the set point and the temperature is 2 degrees Celsius, the valve goes to 100%. If your proportional band is 2 degrees Celsius, and the temperature is 1 degree Celsius, halfway, the valve goes to 50%. It's a straightforward thing, you can easily test it. What integral does is it tries to close that error, because when you have P only control, there's always an error. The valve will open and it'll come down and it'll settle down somewhere. So usually with proportional only control, there's a bit of an error between the set point and the process variable. And integral's job is to correct that error. So what integral does is it just simply says, are we on set point yet? No, open the valve some more. Are we on set point yet? No. Open the valve some more. Open the valve, open the valve, open the valve, open the valve. So integral over time just opens the valve or the damper or whatever it is, or increases the VSD speed more until it closes the error and we're close to set point. Now, that's a very basic example. PI tuning is much more complicated than that, or a little bit more complicated than that. But for the purpose of this video, that's probably enough. So let's put that to the side for a moment. Let me explain to you why this is a problem. Now, let's look at an air handling unit for a moment where we have supply air temperature control. So here's the air handling unit, here's the heating and cooling valves, the heating and cooling coils, some duct work, and the supply air temperature sensor is 2, 3, 4, 5 meters down the duct run. So when the cooling valve opens 10%, and a little bit of water goes through the cooling coil, and it transfers that coolth into the air, and the cooler air goes down the duct, the supply air temperature sensor will detect a slight drop in temperature. So with a supply air temperature control loop, as the cooling valve's opening, there's a delay. Let's say there's 3 minutes from the cooling valve opening 10%, the water going through the coil, the supply air dropping, and the sensor measuring that change in temperature. It's a 3-minute delay. But there is a response to the temperature changing when the valve opens or closes slightly. However, if the temperature sensor is not in a good location, that doesn't work very well. So with zone temperature sensors, where the VAV damper opens slightly, or the fan coil cooling valve opens slightly, more cooler air goes through. First of all, it's a very long delay, let's say 10 minutes maybe, from the cooling valve cracking open to that zone temperature sensor measuring a slight change in temperature. And if that zone temperature sensor is not in a good location, Integral will continue to wind open the output. So the temperature in the zone, 10 minutes away, are you on set point? No. Open the cooling valve. Are you on set point? No. And it opens and opens and opens, and it can wind open the cooling valve too much, or the VAV damper open too much. Now let's have a bit of a discussion around all the different things with regard to a terminal unit that can result in or cause the zone temperature sensor not to be an accurate representation of the load. Now I just wrote down a few examples, and I know that it'll take me 15 tries to get this right. So I'm going to read these off my notes so I can save myself about 20 minutes on this little piece here. So the first thing is, with the perimeter units, it's quite often that the zone temperature sensor has the sun shining directly on it. So the VAVs or fans on the perimeter, often that zone temperature sensor location is not a good indication of the actual temperature because the sun is shining through it from the glass. Supply air diffusers blowing supply air directly onto a sensor happens a lot. So the sensor, it's just below the supply air diffuser, and that cold air is blowing straight onto it. It's not a good representation of what the temperature is sort of over here. My favorite one, where the plasterboard wall that the cable runs down, you drill a hole and you pull the cable through and you install the sensor on there. Most times when I do an inspection, that hole has not been blocked with silicon, which means that that void in the wall, in the plasterboard wall, the dry wall, if that hole's not blocked, a little bit of air can drift through there into the sensor housing and affect the temperature reading. Only a little bit, like 0.5 degree Celsius, so not a lot. So in summer, slightly warm air drifts through, and in winter, slightly cool air drifts through. So if you don't block that hole where the cable comes through, that affects your temperature sensor reading through the seasons of the year. And that's why I'm also not a fan of calibrating zone temperature sensors, because we are often calibrating out that error, that mistake in the installation. Sensors on cold concrete columns, get them all the time. I'm doing an inspection, I'll walk through a new construction site, put my hand on the concrete column, and it's quite cold. And the temperature sensor, the little element, can just pick up that little bit of coolness radiating off the concrete column. So your sensor reads a 0.5 degree or 1 degree less than the rest of the temperature in the zone. The temperature sensor is not accurately representing the temperature sensor in the zone. Recently, last year at an inspection, I saw temperature sensors installed on the ceiling because there's a big open area and there wasn't walls and things. They had to put the sensor somewhere, so they're stuck on the ceiling. That is a very bad place to install a sensor. I reckon if you've got a 30 or 40 story commercial office, there's going to be 5 situations or more where the temperature sensor is rolled up in the ceiling, because through the years of doing fit out projects when they're moving walls around, the mechanical contractor may not have engaged the incumbent BMS company to do disconnects, reconnects, relocates. They just use their mechanical electricians. So sometimes the sensor is rolled up in the ceiling still. Then there's the usual thing where sensors are not in the optimal location because there's a TV there or a whiteboard or glass walls or a bookshelf or something like that. And a great example there is shopping centers. You go to shopping centers, we have VAV boxes in the tenancy. There's clothes everywhere and all sorts of stuff. The sensors are behind things. You can't even find them. You look around, you can't even find the sensor. It's behind something. The other one that doesn't happen very often, I've noticed, is just a sensor installed in a dead spot in a room. So in my office here, if I had the supply air diffuser in the corner there, and the supply air was blowing through and it was coming out the return over here, so this was my sort of my air change path like this, and the sensor is in that corner of the room over there. Not usually a problem, but I just have had some unique situations where the sensor's not reading quite right and there's temperature complaints because the sensor is not in the path, the return path of the thing. But the bottom line here is that there's a lot of things that will result in a zone temperature sensor not being a good reflection of what the zone temperature actually is. Lots of things. And in many cases, that list that I just read out, which I just wrote down this morning, there's probably more. There's probably 2 or 3 of those things that are slightly affecting the reading of the sensor. So, if your sensor is not in a perfect location, which is not possible, then when that cooling valve opens on the fan coil unit, or the VAV damper opens on the VAV box to let more cold air through, it's not going to be measured by the sensor. The sensor won't really measure that 10% valve movement. Didn't even notice it. Another 10%. Didn't even notice it. So integral is going to wind that open. Cooling valve open, more. VAV damper open, more. Integral will wind that out. My notes says here, I could draw the sensor on a floor plan. There's no time for that. I want to go to swimming training. So let's have a think about that, right? A VAV damper being 10% open more than it needs to be, that's not a lot of saving. But obviously, there's 500 VAV boxes. So you multiply that little 10% by 500 VAV boxes. That makes a difference because obviously, if all the VAV dampers are a little bit too open, then the AHU supply air fans and the return air fans are running a little bit harder than they need to get more pressure into the system. So that's the first place where you save energy, is that if you just set all the integrals to 0, then all the valves close a little bit, and all the dampers close a little bit, and then the chilled pumps slow down a little bit, and the AHU fans slow down a bit, and the return fans. That's the first saving that you make. The second saving is that here in Australia, almost every single air handling units and our chilled systems, we have dynamic automatic pressure resets. So the air handling static pressure reset is being reset on the demand. I know this is also starting in other countries as well now. But the point here is that, let's say your VAV damper, the integral is pushed open more. A lot of the AHU static pressure reset strategies, they look at the VAV damper positions and they'll reset that set point. So if those dampers are open a bit more than they really need to be, then it means that we're going to be resetting the pressure set point up to get more pressure into the system, more than we really need to get into the system. All right, I need a bit of a break there to try and get my head around where we're at with this. So hopefully I've convinced you that with terminal units where we're controlling to the zone temperature sensor, if it's not in a perfect location, which it never is, integral is a problem. So hopefully you're convinced of that. Let's move to the next part of this video. So this is what I do and what my specification says. The temperature set points, the cooling temperature set point needs to be 23 degrees Celsius. And the heating temperature set point needs to be 22 degrees Celsius. 1 degree proportional band, 0 integral. So with 0 integral and a 1 degree proportional band, it means that with a set point of 23, with a 1 degree proportional band, the cooling valve will be fully open at 24 degrees Celsius. And with a heating temperature set point of 22 degrees Celsius, a 1 degree proportional band will give you full heating at 21 degrees Celsius. I have specifically chosen those set points and that proportional band because in Australia, as far as I know, all of the contractual agreements between the landlord and the tenant in commercial offices is that the landlord needs to provide air conditioning between 21 degrees Celsius and 24 degrees Celsius. So with the set points I've just told you and the 1 degree proportional band, it's quite neat because it means that if the temperature is 24, I know I'm on full cooling. And if the temperature is 21, I know that I'm on full heating. So I've removed the integral, but I've shortened the proportional band. I think most BMS companies would probably have a proportional band of about 2 degrees Celsius and then have the integral. With a 2 degree proportional band, it means that when you get to the least condition, the 24, when you're out of the least condition, you're in breach of the contract, it means that the cooling valve is 50% open and they use integral to pull it back. But we're removing the integral because integral is bad. So we have to shorten our proportional bands down to 1 degree. So I've chosen a proportional band and I've chosen a set point that works within the least conditions, which is what we need to sort of abide by. Now here's the important part. Here's the very important part. If the set point is 23 degrees Celsius, we don't need the temperature to be 23 degrees Celsius. That's comfort control thinking. We need the temperature anywhere between 21 and 24. Tick in the box. We've met the landlord's obligation to the tenant. We don't need 23 degrees Celsius. 23.5 degrees Celsius is great. 23.6 degrees, 7 degrees, 8 degrees is great. As long as we're under 24 degrees Celsius in summer and above 21 degrees Celsius in winter, that's good. And this is a failure, well, not a failure, but you know, with BMS companies or BMS engineers, you give a BMS engineer a process variable, temperature, pressure, CO2, CO, whatever it is, you give them an output, dampers and valves and speed drives. Us as control engineers, we just want to have the process variable as close to set point as possible. We love controlling things accurately and tightly. We're going to tune those PID loops, control, yeah. We want to have our temperature sensors, our temperature readings exactly on set point. That's comfort control logic. We don't need that. We don't need it to be on set point. We just need it to be below 24. So we remove the integral, we adjust our proportional band settings, and as long we allow that temperature to be 23.1, 23.2, 23.5 is great. In fact, if I was doing a review of a BMS, I looked at the graphics and I saw all the temperatures that were like 23.0 degrees Celsius, I'd be thinking, man, we are wasting energy here for no reason. We don't need 23. 23.5 is good. 23.8, it's getting tight, that's good. If every single BMS service technician in the world went out there over a 12-month period and made these slight minor changes, basically just removing the integral action, double click, adjust it to 0, enter, change to 0, and adjust the proportional band to 1 degree Celsius and adjust the temperature set points, I think that would save a massive amount of energy worldwide in commercial offices. And I'd even sort of like exaggerate the point to say that it might even be noticeable. Like the whole world, we're using less power. Like, I know it sounds ridiculous, but how many VAV boxes and fan cornets and chill beams and heat pumps and package units are there in the world? Hundreds of thousands of them around the world, hundreds, million of them, I don't know. And what if all of them, the valves and the dampers, they all just closed 5%, that one 10%, that one 3%, whoa, that one changed 15%. That is humongous. And it would cost us not a lot to do it. It's just a little bit of hours, a bit of service time to do that. We're not buying chillers and LED lighting. We're not buying variable speed drives. We're just tapping on the keyboard. And we're saving energy worldwide. Like, frustrates me so badly that we don't do these things. Do you know why we don't do this? Or do you know why we haven't done this? Because we do not train our BMS service technicians in advanced topics. We're not even trying. Anyway, see down in the description below for more information on our professional development plans for BMS service technicians, because they're very important. Maybe the most important person in the BMS company, and obviously also design engineers. Thank you for watching, and I will see you in the next one. My note says here, I could draw the sensors on a floor plan. There's no time for that. I want to go to swimming training.